Es una iniciativa llevada a cabo en el contexto del grupo de investigación de física matemática y geometría algebraica, y la idea es que tengamos unos coloquios de forma constante, pues 1 o 2 veces al año, en el que permitamos traer expertos en física matemática, geometría algebraica, pero que puedan dar una perspectiva distinta de estas áreas de investigación y abrir nuevas líneas de trabajo. Y en ese sentido hemos creído que el profesor Yang Hui-he del London Institute of Mathematical Sciences y la Universidad de Oxford es la persona idónea para inaugurar este ciclo de coloquios. Así que nada, muchísimas gracias a todos por venir y espero que esta iniciativa pueda hacerse mucho más tiempo. Y cedo la palabra a mi compañera, la profesora Eva Miranda, que es la investigadora principal del proyecto que ha permitido soportar esta iniciativa. Muchas gracias.
Muchas gracias por la presentación, Ángel. No sé si se oye. ¿Se oye? Sí. Le he dado, pero no va. A ver. Igual me tengo que... Ahora sí. Hay que ponerse aquí en plan cantante de rock. Bueno, es un placer para mí estar aquí de nuevo en la Complutense de Madrid, colaborando con mi colega Ángel González Prieto, y particularmente hoy tenemos un invitado de excepción, el profesor Yang Hui-he. El profesor Yang Hui-he tiene una marcada trayectoria internacional, involucrando diversas universidades con prestigiosos puestos. En particular, ha sido hasta ahora asociado a la Universidad de Oxford y juega un papel fundamental en el London Institute of Mathematical Sciences, que está afiliado a la City University. Antes estaba la City University of London. Ahora la Royal Institution ha dado un paso adelante y ha dijéramos, financiado el London Mathematical Institute. Además, es profesor asociado en la Universidad de Nankai, es experto en geometría algebraica y es experto en introducir técnicas de machine learning en geometría algebraica y en combinarlas. Y hoy está aquí pues porque nos ha parecido muy importante incorporar un punto de vista nuevo, de hecho también ligado a nuestro proyecto de investigación, y está aquí para hablarnos de el matemático, no sé cómo traducirlo, I don't know how to translate the title, the AI mathematician, the mathematician who is an artificial intelligence, o hay el juego de palabras y lo dejamos abierto. Sería el matemático que es también de inteligencia artificial o la inteligencia artificial matemática. Hay las dos traducciones. Y de hecho ahí está un poco la discusión del tema. Entonces es un placer escuchar la charla. La charla tiene un carácter de coloquio, pero si tenéis preguntas a lo largo de la charla podéis preguntar, o al final tendremos una sesión de preguntas que también incluirá las preguntas del público que está en YouTube, que espero que haya mucha gente conectada en YouTube. Okay, I think we are done.
We are done. So, thank you very much, and the stage is yours. Thank you.
Thank you very much. Should I stand or?
As you prefer.
Okay, that's right. Okay.
You are connected, no?
I'm connected.
So you can move, you can do whatever, you are free.
Okay, great. I'm free. I can run. I escape. Right. Thank you very much for this kind invitation, and thank you, Eva, and thank you, Ángel, for having me. This is my very first visit to Complutense. I have many friends in Autónoma, so I've been to Madrid several times, but my first time here, so thank you very much for having me. I'm going to give a talk about... I see some some old friends in the audience as well. About an explanation of Eva's question. What I'm going to talk about is how AI can do mathematics, not how mathematics can help with AI. I'm not an AI expert, but I'm an amateur AI person trying to do some mathematics. So I try to divide mathematics as 3 approaches. Right? I think it's self-evident that you can think of mathematics as a bottom-up, what I call bottom-up. This is to borrow words from physics, really, as a formal logical system. And I will explain a little bit about what I think mathematics should be as a top-down, sort of as a creative and intuitive art. And I will explain why top-down in a minute. and then mathematics from an outsider point of view, or sort of as meta-mathematics, as a language. So let's start by first, completely stating the obvious fact that the 20th century, computers have become an indispensable tool in mathematics. And this is clearly true in things like speeding up computation. But what is more interesting is that it is becoming crucial to a number of important theorems. There are theorems in mathematics which are simply not checkable by humans anymore. Fundamental theorems. Four-color theorem, it came down to 10,000 cases. Even the Kepler conjecture, when Hales proved the Kepler conjecture in 1998, it also came down to thousands of cases he had to check. And what's very interesting is that there's a formal acceptance of Hales' proof of Kepler's conjecture because it's been entered into the computer and then run from the beginning using software like Lean, and I'm going to talk about in a minute. What's I think really striking is the fact that the classification theorem of finite simple groups, this is as fundamental as it gets to mathematics. There's no living human who has actually read the entire proof. And it's inconceivable for the bits and pieces here and there. I know this community very well. And the definitive text is by Gorenstein. And it's several volumes of somewhat distilled. And my friends in this community tell me when these people are dead, and they are dying one by one, Conway, Mackay, Norton, and it's a fact of life. It's very sad. But when Gorenstein and then these people are gone, that's it. There is no longer a student could possibly understand that entire field anymore. All the details, I mean. A rough idea, yes, but all the details, no. So that's actually quite interesting that not only is computers helping mathematics, but it's inconceivable to do mathematics without computers in the next century. And this is not what I'm saying, but this is really said by many, many experts like Buzzard and Davenport that I will mention in a minute. So let's go to the first bottom-up approach of mathematics. So given this challenge of what mathematics is, and this is a problem that was realized as far back as the 20th century, and really you should go to Russell and Whitehead's Principia Mathematica, and well, maybe you should even go to Frege and Leibniz. Leibniz was thinking about his binary computing machine was trying to formalize mathematics. And so they wrote Principia Mathematica in the 1910s, but of course that program was killed by Gödel and by Church and Turing because of incompleteness and undecidability. But, again, so two buts cancel each other. And I love this wonderful quote from my very distinguished colleague, Professor Min-Young Kim, who is a very famous number theorist. He says that the practicing mathematician hardly ever worries about Gödel. Unless you're a logician, if you have to worry about Gödel in your day-to-day life, you're going to go crazy. Because, is my statement decidable or not? I mean, there's a bit of an exaggeration, but there are trillions and trillions of interesting statements in mathematics that are decidable, either by humans or by machines. So we don't have to really worry about the ones that are not decidable. Of course, we do have to worry about them, but not all of us do every day. So what that has engendered really is this ATP program. It's really a program that started in the 1950s. And very interestingly, this is around about the same time as neural networks. The first neural network was 1957 in the basement of, I think, Penn or MIT, where they built photoreceptors from cadmium sulfate. I don't know what cadmium sulfate is, but it sounds interesting. And they put this stuff on a wall, and they shine light at it to try to stimulate it like a neuron. And they were actually trying to do computations with it. So these guys were doing very similar things, Noah Simon Shaw in the 50s, what they call the logical theory machine. And they were actually taking axioms from Principia, and they were able to prove simple statements from it, by shining light on a wall. How they did it is amazing. I have no idea. But this really progressed with the advent of type theory, and then homotopic type theory from Vygotsky. And I don't understand any of it, but it is a language for computers that is well adapted for computer program. And the computer programs that do it now are things like Coq and Lean. So Koch was able to prove the four-color theorem in 2005. By proof, I mean to check, you'd put every single intermediate step of the proof in type theoretic language, and then hit the return button, run, wait an hour, have a coffee, come back, and it's proof. It's good. And likewise, I mean, this is getting very, very important theorems, right? So there's the four-color theorem, and then Phi-Thompson, which is the odd-order solvable group theorem, for which Thompson got the Fields Medal. And this was rechecked using Koch in 2012. And then the one that's really interesting is Lean, which started in 2013. 10 years down the road, Lean now has all of undergraduate mathematics symbol by symbol. And it was checked last year. So this Lean, the champion for Lean is Kevin Buzzard at Imperial. And he hit the return button, and he checked all of the undergraduate mathematics, and it's good, it's consistent. So these Weierstrass theorems, you've been taught, it's all good. Dirichlet, it's all good. And so there's no inconsistency. The reason why Buzzard mentioned this, because I love these two talks, both by Davenport and Buzzard, and highly encourage you guys to watch it. These are the two ICM addresses. And Buzzard is a fun guy. He begins many of his talks with two side-by-side abstracts. These are abstracts from the Annals of Mathematics, which is arguably the most peer-reviewed journal of all human history, right? Of all of science. This Annals of Mathematics, these two abstracts state contradictory statements. So at least one of them is just wrong. So Kevin likes to use this as an example. You can see this on YouTube. He says these two, we don't even know. We can't even check it. Because it's impossible. It would take a longer lifetime for somebody to sit down to check it. So we need Lean to be inputted, all of the background knowledge of these two papers, which is we're not there yet. It'll take many, many more years. But once we have it, we need to check at least which one's wrong, or maybe both. So, so of course, then DeepMind gets involved. So DeepMind got involved in this in last year. I'm in regular contact with DeepMind because they're 30 minutes away from our institute. They're in King's Cross. And Szekedy from DeepMind, which in the view of Kevin and Davenport, is that it's way over optimistic. Despite the fact that I'm telling you all this negative stuff, this view that computers will beat humans in proving theorems by 2030 is very, very overly optimistic estimate. So we're not out of the job in the next 7 years. Maybe 50, but not 7. So Kevin is like, we're not, Lean has only undergraduate level, that's 0.1% or less of mathematics. So, and we can't even put all of things by hand and start checking. And then once we have it all in, we still have to find pathways to find new proofs. Now it's just, Lean is just a repository of all statements. It doesn't know how to search path of doing mathematics. So that said, so this is the first way, so bottom up. Well, I won't talk much more about it. And then this meta-mathematics was very interesting. Of course, everybody's talking about ChatGPT. ChatGPT has passed the Turing test. This is kind of interesting. I think this should be, it's not really emphasized, but it's indistinguishable from talking to a human now. So the main feature for us is there ChatGPT for math? And stories have it that this is the reason why Sam Altman resigned and then was reinstated. It's because of OpenAI's Q-star system, which is supposedly a large language model for mathematics. And I don't know the details because they're being very secretive about it, but it should appear at the end of this year or maybe in January. Q-star should be able to reason mathematics using large language model. And I don't know, I presume they trained it on the archive. So we trained it about a few years ago before we knew what we were doing. This is a kind of interesting exercise. We took this, my friends and I, Jajala Nelson, we took 6 sections from archive and we just downloaded the titles. It's 3.6 million titles, and you just do linguistic analysis. We were able to find interesting stuff in the ones that we did theoretical physics related stuff because my friends were theoretical physicists, and it found some very nice true statements like word2vec is you map languages to a vector space. You can do addition well, it's not a true vector space you can't scale, but at least you can do vector addition, vector subtraction, and you find the identities like string theory plus Clabiao is equal to M theory plus what, and then you find it fills in the what as a G2. So that's actually kind of nice that he finds. He also finds other nonsense as well, but it's okay. But I presumably this is what Q-star should be doing at a much, much, much more advanced level. Just one thing to mention is that we took archive, which is, we know archive, but people may not know what Vixra is. Vixra is archive spelled backwards. So Vixra contains all of the papers that are rejected from archive. So Vixra has things like proof of the Riemann hypothesis, a 2-page proof of Fermat's last theorem. Einstein is wrong, the usual stuff. Quantum mechanics is wrong. So it's complete nonsense. And we were able to at least distinguish, just from a large language model, that the titles alone are distinguishable. So the titles here have a very good structure within different sections of the archive. But within Vixra, it's a complete random distribution. So they have the right words, but they don't even know in their title to put the right sequences of words. So just from titles, from abstract, you'll get something. But at the time we were doing this as a joke, but then this Nature paper of Chitorian, when they did this 3.3 million material science abstracts, they were able to find new reactions that are actually better than human, In other words, material science in some sense is finished. You don't need this field anymore because a large language model can read abstracts and conclusions in that branch of science faster than humans and then discover new things faster than us. Mathematics is much harder because the linguistic structure of mathematics is much more subtle than something like material science. But I suspect for material science, maybe in 20 years, that field will be replaced by AI scientists. Mathematics, we're still safe for maybe another half century. So I won't say much more about this, but what I really want to tell you about today is what I try to call as top-down mathematics. So we've got bottom-up, meta, and then top-down. So what do I mean by top-down is that, how mathematics is actually done. We don't really, the working mathematician, by mathematician I mean the general mathematical science, including theoretical physicists, we don't write definition, lemma, theorem, proof, corollary when we're working. We doodle and we try to make some computations and make some nonsense and scratch. Once everything is perfected, we write our papers backwards with definition, lemma, right? It's all done. And this is a great example is that the Bourbaki way of writing mathematics is completely not how we do it. It's because it's written backwards. And nobody thinks of mathematics. In practice, we don't write. These definitions are so abstract that we certainly don't do that. We write these definitions after we've played around with thousands of examples. Then we write good definitions. And I think nobody can dispute this. But then we write it to make it look very Bourbaki style, which has somehow become the standard culture. But the idea is that a lot of mathematics starts with intuition and experience and experimentation. Right? And this is what we do, in the hundreds of examples where formalism comes later. So as great examples, I like to emphasize this joke. What is the best neural network of the 18th and 19th century? Well, it's clearly the brain of Gauss. It's not an artificial neural network. It's a human neural network that was better than any other neural network of its time. So Gauss was able to look at this graph at the age of 16 and say, well, this is clearly x over log x. This is the prime counting function, the number of primes less than or equal to x for real number x. The interesting is that he was able to do this. Of course, I think he was inspired by Legendre and Dirichlet, but he was able to just say this is this. But in order to prove this, you need complex analysis. At least the first proof of this needed complex analysis. And that wasn't invented until Riemann came about, and Cauchy later. And then Adamad was able to, and Delaveille-Puissan were able to prove this. So Gauss was just new, right? So top-down mathematics needs something of an AI input which knew. How do we know with this kind of experience to say this looks like x over log x? Right? This is just a classic example. Another famous example, of course, is the BSD conjecture. The BSD conjecture of course, it's a Millennium Prize problem, but what's not emphasized enough is that the BSD conjecture came from experimentation. Birch and Swinnerton Dyer locked themselves up in a basement in Cambridge using a computer the size of this room that had maybe like 1 megabyte of RAM or something. And they just plotted, the way Gauss did, ranks and conductive elliptic curves, and then say, oh, I think the order of magnitude, of course, based on vast human intuition and knowledge, and you should be plotting things like this. And you see that, and I'm going to mention BSD later in the context of this AI-guided mathematical discovery. But it's interesting, right, that they were, so what I want to see, you see a pattern here. Back in the 19th century, the human eye was good enough to look at something like this and say it's x over log x and conjecture a fundamental result in mathematics. Already by the 20th century, in order to hit something fundamental in mathematics, the human eye wasn't that great anymore, in the sense that anything that could have been done by the human eye was done by Gauss and people like that. Well, I mean, not all. It's a huge exaggeration, but I mean, you need the next level up. So you need computers to help you to do this, right? Gauss was amazing, right? He was doing this plot to the millions by hand. He had to compute with a combination of looking at tables and doing computations by hand. But that kind of stuff was sort of replaced by the time we're into the mid-20th century, that you have computers to help us to make these conjectures. So in some sense, top-down mathematics is, in a way, conjecture formulation in mathematics. And how do we go to the next level? From Gauss, the human, the best neural network human, to BSD level, which is computer-assisted conjecture formulation. And now in the 20th century, and what I'm trying to argue, and I'll tell you now, is the next level is AI-assisted computer mathematical discovery. And once we have this should be in tandem with bottom-up mathematics. Once you know what you're trying to prove or raise interesting conjectures or directions of research, you should type that into Lean and then have Lean try to prove theorems of this type. At least it's the long, right, this may happen next century, but this is where I think the field is going. At least talking to people like Kevin, and increasingly this discipline. So I love this quote. Just to emphasize that, people think of data science as a 2010 thing, the first decade of the 21st century. But really, even in mathematics, the computer and data-driven mathematical discovery and mathematical, detection and discovery and proofs go way back. So there's a long tradition of doing so. So now let's play some games, right? In terms of conjecture formulation. Right? Well, if I gave you this sequence, you can probably immediately tell me what the next number is. Right? Yes, so it's a multiple of naught. If I gave you a sequence like this, it's a little harder. You can take a guess, since I've been talking about prime numbers. So this one is just 3, 5, 7, 9. So all the odd integers, if its prime is 1. So it's prime characteristic for the odd numbers. So after a while, you can probably struggle and get the next number. So I mean, putting in increasing difficulty, this one looks pretty random. So I will spare you the pain. This one is the parity of prime factors up to multiplicity. So it's essentially a shifted version of the Liouville lambda function. So the idea is, so humans are very good at this immediately. Humans, we could struggle a little bit with this. And this, okay, so actually, so there's money to this. So if you can predict the next number, Peter Sarnak will be very happy. He will give you some money. And in fact, if you can predict with the next one, it's equivalent to the Riemann hypothesis. So there's a version of the Liouville lambda, some asymptotic growth rate of the Liouville lambda that's equivalent to Riemann hypothesis. So obviously simple, medium, very hard. Now, is it true that an AI system would pick up these patterns just as much as humans would would. So again, I love quoting Hardy. I think Ava loves quoting Hardy. We all love quoting Hardy. So Hardy gives a wonderful definition of what mathematics is. And what is interesting is that perhaps the one thing, well, for sure the one thing, and perhaps the only thing that an AI system at present can do better than humans is pattern detection, for sure, because we can only visualize up to 3 dimensions. If a problem involves more than 3 dimensions, it's very hard to gain intuition. So the idea of this emerging field in the last 5 or 6 years is to try to get high-dimensional data somehow in pure mathematics and get an AI system to look at the high-dimensional data and then try to make a concrete conjecture. So that's what I mean by top-down mathematics. So let's look at this one. So how do you make this problem into a high-dimensional representation problem? I've chosen this problem to be very binary because to make life easy. I don't have to. I could actually write down the actual Liouville lambda or could actually write down the actual primes. Right? But let's just make it all binary because binary is a very good thing for computers to do. So what you can do, one thing you can do, is to turn this into a supervised learning, machine learning problem. Right? So what do I mean by that is that you can take a window, it's a long sequence. If you just want to do sequence prediction using something like a recursive neural network, a recurrence neural network, it's not going to do very well because of the feature. The features are not, they're not enough features, right? You just have these sequences. So sequence prediction is not that straightforward. But you can turn it into something that machine learning algorithms like. For example, I can take a window by window of a fixed size, and then I'm going to associate the next number outside of this window. So I shift again, I shift. Then I can easily create millions of vectors which are labeled by ones and zeros. So now it becomes a problem in a binary classifier for a binary vector, which will be very, very good for adaptable for a machine. So you can try this for these sequences, and then you pass it to standard classifiers. This is just an experiment that I can telling you to do for something that's very, very basic. I'm just doing properties of division. And there's standard classifiers, which I learned. I'm not a machine learning expert at all, but at least I learned these words. There's things called support vector machines, base classifiers, nearest neighbors. You look up. I took a Coursera to learn machine learning. It's okay. It's a great thing. And then you learn about all these algorithms for pattern detection, and pass it to neural networks of some form. Your favorite kitchen sink, throw it in. And is it true that these problems, the 3 problems I mentioned before, when rephrased as a binary classifier, will behave the way that you expect to? And indeed, very quickly you'll find that any of these classifiers would do the first problem to 100% accuracy and 100% confidence very quickly. So the second number I'm writing is some version of a chi-square. You want to do some. It's a 2x2 confusion matrix, and you want this to be as diagonal as possible. So great. So the mod 3 problem is very simple, and for any of the neural classifiers, we can do immediately as well. Interestingly, if you don't tell it it's mod 3. If you mix up mod 3 versus some other mod 7, whatever, then you get confused and the machine gets confused as well. It's very, very, very difficult. In fact, you go to ChatGPT, at least 3.5, you tell it, give me the, I know ChatGPT 3.5 was already very, very good at solving calculus problems. Right? It's completely correct. Or basic geometry problems. Give me the intersection between this plane and this plane and this, and do it completely correctly. Very rarely will you get it wrong. But if you ask it a simple problem like 7 divided by 11, give me the 15th decimal expansion. It has no idea how to do it because linguistically you can't process it. But ChatGPT 4 and above now bypasses that problem because it links to Wolfram Alpha. So it'll actually do that calculation. So this is getting it. But division is actually not as easy as you think it is. Anyhow, so this one, great. Mod 3 is great. The prime Q is a bit harder. That's very interesting because, if you do this thing with primes, you need to balance a little bit because the primes get rarer and rarer. So at some point, you're just going to hit all zeros if you fix a window. Right? So by balance, I mean you have to stretch a window size to to a factor of x over log x, just to make it as many ones and zeros. And then it actually gets about 80% of them correct. I don't know why it's getting them correct, and I will explain, or I would address this issue about not knowing why it's doing so well later, because it's very hard to interpret what a neural classifier actually is doing. And that is currently the biggest problem with AI systems doing mathematics. Just because a neural network can do extremely high accuracy, you don't know what it's actually doing. Right? With some black box, it's very hard. So this is called the interpretability problem in machine learning. The Liouville lambda is interesting. You get 50%, so that's coin toss, and 0% confidence, pretty much. And as you would expect, because if you can get this number to even higher, Peter Sanak says if you can get this number to 0.51, then you're already making great progress in breaking banks, right? Because this prime factorization, really, there's a lot of it. There is no theorem and no better estimate, even in analytic number theory, to beat the 0.5. If you can find a neural network that beats 0.5, he will give you a lot of money. But then you can make much more money by cracking banks. And then we'll never see each other again. So what is my initial motivation for doing all of this? So I see my old friend Kalin, and he saw me grow up as a student, and I think I came from string theory. So my original motivation was to study Clavier manifolds. So how did I get into this field? Right. So just very briefly of what's the kind of mathematical problems that we were trying to do in string theory, in some sense, from a mathematical point of view, is to generalize this picture. This is a very, very naive statement of string theory, which is, of course, in one complex dimensional geometry, there is this trichotomy of theorems, right? By trichotomy, I mean, you have Fano varieties of general type, and right at the boundary is Ricci flatness. This is a very magical statement. We know there are a finite number of Fano varieties. We know there's an unclassifiable number of varieties of general type that have somewhat Ricci negative behavior. And this boundary case of Ricci flat, why Ricci flat is because it's vacuum Einstein solutions. So in some sense, this Ricci flatness comes from vacuum configurations. So there are beautiful theorems, I won't get into details of this, that links various different fields of mathematics in trying to understand this boundary case of Ricci flatness. Right, so this is an ancient problem in algebraic topology or algebraic geometry. And it just so happens that in higher dimension, of course, in higher dimension, this is very, very difficult, you could imagine. Right? You can't, generalizations of this to higher dimensions you can do, but it's very hard to control. So at least for Kähler manifolds, this is why Calabi's conjecture was so important, is that at least for Kähler manifolds, there is a very direct generalization of this diagram. Of course, Calabi lived to the age of 100, who just passed away, and so he lived a very happy life. And he raised this conjecture, is that for at least for Kähler manifolds, the Chern class controls the Ricci curvature, just like the way that you would see this for complex dimension 1 in a classical case of Riemann surfaces. And of course, he showed the uniqueness of the existence of such metrics, but he couldn't prove the existence. So Yao proved it in the 70s, and he immediately got the Fields Medal for it because it's such an important context. Because what Calabi was doing was, Calabi and many people, was to make a high-dimensional analog of something so familiar to us, which is Riemann surfaces. And it just so happens that in the 1980s, Yao was next-door neighbors with string theorists. This is why I believe in string theory, fundamentally, because it has interesting mathematics. I have absolutely no idea, and I don't think about ever whether string theory is a theory of, fundamental particles, even though I'm putting this slide on. So string theory, if you don't know what it is, in one paragraph, it's a theory in high dimensions, usually taken 10 or 11, in which you try to reduce, we don't live. This is a theory of quantum gravity in 10 dimensions, and you can ask Colleen actually more about what actually string theory is. But string theory is this high dimensional theory, and we don't live in this high dimension, but it unifies quantum gravity, unifies quantum field theory with general relativity, and we have to try to reduce dimension in order to get to our observable world of particles and galaxies. So it just so happens that physicists were thinking about this in one context, and then around about the same time, mathematicians were thinking about this generalization of of Calabi's generalization of algebraic varieties in complex algebraic varieties, and it just so happens that these guys also somehow hit on a Ricci-flat Kähler condition for these manifolds. It's not the only solution, I want to emphasize, but they hit on the first solution that was a solution to this. So in fact, it was these physicists who then called Ricci-flat compact, smooth, Kähler manifolds as Calabi-Yau. It's kind of interesting that came from physics. Calabi obviously is not going to call it a Calabi-Yau. Yau's not going to call it Calabi-Yau. So you need some other physicist, someone else, which in this case turns out to be string theorists, who named these manifolds to be Calabi-Yau. And it just so happens that Strominger was Yau's neighbor at the Institute of Advanced Study in the mid-80s that allowed this conversation between physics and algebraic geometry. So this was the context, and I won't bore you a lot with this. Okay, I'm going to skip philosophy. So I'm going to skip all of this because at least you should see what the masters say. There was this famous Wigner paper in 1959, who tries to emphasize why is mathematics so effective in the natural sciences. And in 2010, Atiyah and Hitchin and Dijkgraaf tried to answer this by saying, why is physics so effective in pure mathematics? And I think this is the reason, at least, I like doing string-related problems, because this is a one branch of physics that's constantly giving new and exciting problems to mathematics. Anyhow, this is just a distraction. So let's go back to, so that's how I got into this problem, is that, you want to compactify on these Calabi-Yau manifolds, right? But the interesting fact is that in the last 20 years, so because of people like Kreutzer and Schaka, who are physicists, they started cataloging Calabi-Yau manifolds. Mathematicians at the time would never do this, and this is entirely due to, it's the fault of the Bourbaki school. You talk to a card-carrying algebraic geometer, and you ask him or her, can you just give me an example of Calabi-Yau manifolds? And they say, no, we don't think about this, it's beneath me. And then the physicists, we're the dirty people, we have to actually try to create them. But Yau at least is very kind. Yau gave 5 examples of Calabi-Yau manifolds within a year. So you can take the quintic hypersurface in CP4 and so on, they're explicit. Right? And then Kreutzer and Schaka really, and then Philip Candelas and these people who are physicists who took the challenge, let's just catalog these Calabi-Yaus, because you tell us you reduce on these Calabi-Yaus, we get some kind of a universe. What is likely to be the one that creates our universe? So they thought at the time maybe a couple of thousand. Right? So these are complex dimension 3, Ricci-flat Kähler manifold. Seems like a very concrete problem. Right? You think maybe a couple of hundred. I check. Maybe this one gives some nonsense, and I pick the right compactification. Then I solve the problem of the world. Right? That's what they believed in the 90s. Kreutzer, Schaka, and Candelas, they all worked together, and within 10 years they found 500 million. So that's actually a very interesting number. So Calabi-Yau manifolds in dimension, complex dimension 1 is 1. There's only one of them. It's the surface of the torus. Complex dimension 2, there are 2 of them. There's the K3 surface, and there's T4, the 4-dimensional torus. Dimension 3, you think, okay, there's 1 in dimension 1, 2 in dimension 2, maybe 3. But no. Within 10 years, you find 500 million, and it's growing. Now it's easily over 10 billion. Schaka has just taken. So we don't even know how many there are. Yau's conjecture says that within each dimension, it's a finite number of possible topological type. But that's just a conjecture. So, but it's nice even for pure mathematics, because it says that we know infinite varieties is always finite. So positive curvature is always finite. But this boundary case of Ricci-flat Is it infinite? In a good case, it's finite. But this finite comes at a cost that it's 10 to the 10 to the multiple ones just on topological type. So that's the background, how I got into this. Well, then I started saying, well, around about 2017, I learned from, but at least in 2017, a lot of our my friends and colleagues and former students and postdocs immediately went into machine learning. After they get their PhD, forget about academia, I'm going to make a lot of more money doing machine learning. So I tell them, what is this thing called machine learning? And they explain, I learned from them. And they say, well, machine learning is just basically, in some sense, very glorified pattern recognition. But, okay, at the time I was like, oh yeah, but this is pattern recognition. But now it's actually a very, very powerful tool. So, in a typical computation in string theory and a typical computation in algebraic geometry is to take some polynomial representation of an algebraic variety. You can record, so here what I've done is multiple complete intersections of multiple hypersurfaces of multi-degree embedded in a multi-projective space. So this is a typical algebraic variety. And then you compute by chasing exact sequences until you cry, you get some topological invariant. This is a typical computation. But we have lots of them now, right? We now even have hundreds of millions of them. You can take some samples of them and try to see how well it predicts, exactly in the way that I was doing with this binary classifier. We know the binary classifier was struggling a bit with Riemann hypothesis. It wasn't struggling at all with division modulo 3. Where does algebraic geometry sit? So at the time I just put this as an image process, and you can convert anything here, a tensor of any type to a proper image, and use some very naive network. And now Finatello and many various people have improved this vastly. Now they use inception neural networks to just do this problem, and they're getting 99.99% accuracies. So in some sense, algebraic geometry over C, I don't know, over FP, I don't know, but over C is very, very amenable to machine learning. And that's the first take-home thing. So I'm going extreme. I'm going completely fanatical. I'm going to say algebraic geometry is an image processing problem. So far, I have not been killed for saying this. I've said this in front of many algebraic geometers who have not beaten me up and come upstairs and come up and beaten me. They say, oh yeah, it's true. Algebraic geometry is an image processing problem. Okay, and so I'm also barricaded from this. I can hide. But then what got me thinking is that how much of mathematics is not an image processing problem? Right? So when you go back, of course, in some sense, mathematics is. By definition, it has to be. Because it's a pattern recognition problem. Any problem in mathematics is a pattern recognition problem. You can most likely translate into an image processing problem. And so now let's take that and see how much other problems can we address. So I started going crazy with many, many friends. I made as many friends as I could possibly manage in 5 years. In every imaginable field that I can make friends with. So from physics and algebraic geometry, and I helped a lot by my many talented friends and my talented students. And so we're just trying to map out problems, make a friend. A typical day would be, I go somewhere, I make a friend, and I don't understand your field. And can you explain to me what is the problem that you're working on? Can I translate that into a machine learning type problem? And then try to see. So we mapped out many problems, and so I'm just trying to summarize. I can't summarize the various experiments I've done here, but the key is, oh, by the way, you can buy these books. So it also produced these books, once an editorial of all these experiments, and a textbook on why Clavier manifolds lead to machine learning. Buy them, so I get £50 a year of royalties. So I don't have to sell my liver for my children. But the main take-home thing is this. Sure, it works, and at some point I was trying to establish a hierarchy within mathematics of which problems are good for machine learning and which problems are harder. And these are completely speculative. Algebraic geometry is very good. Number theory is very bad. because it's very difficult to see patterns in primes. If you do, you crack the Riemann hypothesis, right? So somewhere in between is representation theory and combinatorics, but I won't bore you with the details. But the key thing is, sure, you can machine learn this, and you give me a number, right? And you say percentage accuracy in predicting some data that you give me. How useful is it? And how do we evaluate, how do we extract real mathematics from a black box like this? So I'm actually running a conference right now in Cambridge with my collaborators. Sorry, it's becoming too blurred. My many friends here, Suresh, and so we run a conference called, actually this is just part of the title. It's called Black Holes, Bridges Between Number Theory and Holographic Quantum Information. I don't know anything about any of this stuff. And then it's also and machine learning. It's basically to get many friends. But we were very happy that Buzzard came. And more importantly, we got Birch to give a lecture. Birch is 90, so he had to give it over Zoom. But during this thing, we're mucking about with this. So together with Birch, Buzzard, and Albrecht Klemm, who is a mathematical physicist, we sort of half-jokingly formulated the Birch test. Now, I think this is quite important test. So ChatGPT has passed the Turing test, right, in the sense that you can no longer distinguish an AI system based on a large language model. We hope that OpenAI's Q star will pass the Birch test in the next few years. But now let me explain to you what the Birch test is. Is that it has to be a conjecture. Just because you learn some data, what can you do? I know algebraic geometry can be treated very well by a deep neural network with 5 million parameters. Okay, fine, it's faster. But one good thing, it is faster. It is faster than doing sequence tracing. If you want to run an algebraic geometry problem on Macaulay 2 or Sage Math, you're going to be completely, you're stuck, because any algebraic geometry problem will, end of the day, be reduced to a Gromda basis computation. And Gromda basis, unlike its counterpart of a linear reduction, Gaussian elimination, is a double exponential algorithm. So you're sunk if you have any complicated algebraic variety. So the Birch test is, it has to be generated by AI, a conjecture or a pattern that's founded by AI. It has to be concrete enough to be a conjecture. Okay, so that's useful for mathematics. It has to be non-trivial enough for the community to work on it. So the Birch sets a very high bar. Birch is the Birch-Swinnerton-Dyer conjecture certainly passes all of this except number one. It was generated by computer, but with Birch and Swinnerton-Dyer telling the computer what to do. So these are the three Birch tests, and most importantly, it has to make Birch happy, right? So what are the candidates for the Birch conjecture, for things that in the last 5 years that have actually passed the Birch test? So we don't really have one, but we almost have one. So the first one is the one that I've been playing around with, the Hodge numbers, the topological invariant prediction for Clapeyron. There you can get 99.99% accuracy. But it's useless because it's not interpretable. I cannot tell you what the neural network is actually doing to make these exact sequences do. At some point, I hope to extract exactly what it's doing. Whatever it's doing is not doing sequence chasing. So it's finding some very clever way to get topological invariance, but we don't know how. So it's not interpretable. It doesn't pass the Birch test. This one I like slightly better, which is we plotted the Cayley table of the first 1,000 finite groups, enhanced with permutation. So this is just some Cayley table. It's defined up to permutation, and you flatten it and you plot it in Euclidean space. So 1 million points, and you would think it's going to be complete, stuff, and you can't even visualize it because it's in dimension, 1,000. And but then we run a support vector machine, which is a good separator. It separates the space of, there's a 1,000 dimensional hypersurface that separates the simple groups from non-simple groups to 99% accuracy. We have no idea why it's doing it, but this should be a very interesting way to do representation theory. But this still doesn't make Birch happy because it's not precise enough. You make this plot, what can you do with it? There's some hypersurface here, and what can you do? So, but this is good. But you could potentially pass the Birch test. if you worked at it, but we don't know. We have to think about. So we just wrote a follow-up paper yesterday, which is maybe it's an artifact of using the Cayley table representation of finite group. What about generators? So we tried every simple group is 2 generated. So we generated random subgroups of Sn, but that are 2 generated. So again, you can generate 1 million points, and you can also see the separation. Why? Don't know. So there's something very, very different fundamentally about a simple group versus a non-simple group. It's kind of interesting, but this is a proto-conjecture because I can't tell you how to actually go about to prove something. There's this famous paper of Davis et al., and this is in collaboration with DeepMind, which appeared last year. And these guys did a very beautiful thing. They used the saliency test to find in a whole sequence of not invariants which ones are the likely features, and they were able to inch out a very precise, which happens to be linear, relation among these various not invariants, which has not been noticed before, and that is good. So this almost passed the Birch test, but it doesn't. Birch is not happy because it's not non-trivial enough. They were able to prove this conjecture within a couple of months. So I mean, Birch's bar is very, very high. I mean, this is okay. It's hard to make him happy. So let me just end by saying that at least there's something that we proposed to Birch that almost made him happy, and this is the memoration conjecture. So this is one that, and the only thing that doesn't make him happy is a conjecture, and this is related to the BSD conjecture. So when I started working with real card-carrying number theorists, and this almost made him happy because it passes non-trivial. It's still working. We don't have a proof of the full. We don't have the full proof of the memoration conjecture yet. It's precise. It is very precise, and I'll show you right now in the last slide. It is interpretable, obviously, but the only problem is that we humans had to intervene in the interpretation of the AI. It wasn't purely, it wasn't like let it run. So let me just wrap up by explaining to you what this problem is. So I won't bore you with this. So the BSD conjecture basically says that there is the analytic rank of an elliptic curve is controlled by the order of the vanishing of the pole of the L function. In this beautiful lecture that Pilar gave yesterday, was just the history of, you guys should have been there yesterday. Professor Pilar Beyer gave this beautiful talk about the entire history of the BSD conjecture from Euclid to Langlands. So anyway, the point is that there's this L function you can compute for any elliptic curve. Elliptic curve, you have this rank, which controls the extent of the infinite count of the number of rational points. And how that is an integer, which is z to some power. And this number should be the order of vanishing of the L function that you compute from the elliptic curve. So that's the BSD conjecture. So when I learned about the BSD, one of the first things I tried to do was with data scientists to try to predict the rank of the elliptic curve using the Weierstrass representation. And we didn't get anywhere. And at the time also it's great because number theory is hard for machine learning. But when I started talking to proper number theorists, they said, well, don't use the Weierstrass representation, but use the L function coefficients, because that's exactly what BSD should be telling you. So just very briefly, if you take an elliptic curve, right, and the L function is just a point count, it's a generating function for the point counts over fp. So instead of trying to find the number of rational points, you count the number of points on the elliptic curve. So y squared is equal to x cubed plus something. You count the number of xy's, which is ultimately you want to know the number of xy's which are rational. Right? That's the Diophantine problem. But instead of doing that, you count it over fp, the finite field. You can do that because you can exhaust it. It's a grid search. In the worst case, because this is a finite field, you just have to check every point whether it satisfies or not this curve. So this is now. So the beauty of BSD of all these theorems of A and Grothendieck and friends is that this generating function captures for you the which is, I mean, this is a number theoretic problem. This captures for you the geometry and the analysis on the elliptic curve. So, but I won't bore you with the details, but here is the coefficient, which is called the AP coefficients. So this is a multiplicative thing. If you take this for a point and not the elliptic curve, this is the Riemann zeta function. So that's why the BSD is a generalization of the ring hypothesis. So if you take this, BSD says these coefficients should know something about the rank. Right, that's the bottom line of BSD. But now, let's put in machine learning. Well, these coefficients you can treat them as vectors. So now you have a classification problem again. You take these vectors and you try to say, can these vectors predict the rank of the elliptic curve? We know it has to by BSD, but we just don't know how well it does. And we were surprised when we actually ran this. Because we're not using the Weierstrass representation, and we're using this representation, you get 100% accuracy very, very quickly. That's interesting. So we know this is true, and it has to work this way. But what is it actually doing? So, okay, I won't bore you with the details of all of this. But the reason we're able to do this is because there is the LMFDB, which has 30 million elliptic curves over Q. It's a wonderful database. And if you take this prediction problem, you get the rank to 100% accuracy, very cool, 99 point whatever. So can we make it interpretable? Right. So what we did is, see, that's why it doesn't make Birch completely happy. It's because we need to kind of manipulate by hand with humans what it's actually doing. So in the end, we actually settled down for this thing. We did a PCA analysis. So a PCA is a principal component analysis. You take these vectors, which are labeled by rank, and you take these vectors and you project it to 2-dimension. Right? That's you project it to maximize variance or minimize variance. And these are the principal components. It was very beautiful to see. Boom! It suddenly shows. So we took elliptic curves rank 0, 1, and 2. So there's a theorem now that almost all elliptic curves are rank 0 and rank 1. So this is what got Bhagavar the Fields Medal. He showed that statistically, almost all elliptic curves are ranked 0 and 1. But in the database, 0, 1, and 2, there's still sufficient representation, enough percentages. And we just did this PCA analysis because we know the neural networks and the other classifiers did so well. Let's try PCA just for fun. And boom, it separated the rank 0, rank 1, and rank 2, just by itself, right? So now we're like, wow, this is kind of nice. Why is this even happening? So, okay, fine. Then we looked at the matrix, the actual matrix transformation of the PCA. PCA is nice because you're taking, we're talking about 200-dimensional data or 500-dimensional data. You take a 500 by 2 matrix. You can look at this, at least some human eye can look at some of them, and you see that it's really honed in on on particular columns. So, and then after some massage, this is what didn't make Birch happy. It's because humans were involved in this. We find that what the PCA was actually doing was to take this average, because it's a linear process. Right? So what is it doing? It's actually being able to distinguish these different ranks by averaging different elliptic curves over a given conductor range. This is something that, for some reason, number theorists weren't doing. Because why would you do something like this? It's a bit strange thing to do. We call this, I think it's called a vertical average, because you're averaging over different elliptic curves, but within a conductor range. And this average is very precise. So then we can make a conjecture. In fact, the conjecture is this average in the space of all elliptic curves should converge to a curve, a precise curve. And in fact, it is scale invariant with respect to the conductor range for some reason. So this is now, Andrew Sutherland, who runs LMFDB, is wonderful in this. And we tried, 100,000 points. And it's like, ooh, we can do 100,000. He says 10 million. So he did 10 million, 100 million. So he was able to do that very quickly, assimilate these points. And so when we call this the murmuration conjecture, because we took 100,000 points, and they would see it reminded me of well, because I was working with real experts in number theory, I'm by no means an expert, but my biggest contribution to this project was to say, they say, well, this looks like something. I say, you mean the memoration of Stalin's? So I say, okay, great, let's call the paper memoration. So I contributed something, which is like the memoration type. But the point is that this memoration behavior should disappear in the infinite limit, and it should converge to a curve, to precise curves. So the memoration conjecture has now been proven for Dirichlet characters of L functions. And this wonderful, Lina Zubrilina have proved this for weight 2 modular forms. And you can actually, it's a curve, you can actually see in the, and she showed analytically what this curve should be. And so there was a conference just in July, just dedicated to what this memoration so this is, what I'm trying to say here is, it passes the Birch test is that it's AI generated, it's non-trivial, it's precise, it's non-trivial because people are still working on it. You know, every once in a while now you see another paper on proving this part of the memoration conjecture for this. But the only thing that didn't make Birch completely happy was because humans were actually involved in the machine learning interpretation. But that's pretty good. I mean, he's almost happy. He's a 90-year-old man. It's very hard to make a 90-year-old man happy. I don't know. Maybe it is easier, you know, to make a. So just sorry to take so long, but just to end. So it's clear that the way of conjecture formulation, the eyes of a great neural network in the 19th century is good enough. The 20th century, you need computer-assisted conjecture formulation. But I think in the 21st century, you really need AI-guided. By AI, I mean very sophisticated. I mean, at some level, AI is just a very sophisticated computer algorithm. But you need something more than just, oh, let's plot this with a computer and see what happens. But you need something more sophisticated, like PCA analysis, to be able to make interesting conjectures. So, yeah, so in some sense, the future, and I'm really, really looking forward to the new year where ChatGPT, OpenAI will give a new version of this, and let's see how this will do in terms of sort of a meta-analysis of mathematics. So, thank you very much. Oh yeah, and there's this wonderful quote.
Thank you very much for the talk. Are there any questions, comments?
Yeah, please.
Several questions. The first one is purely
¿Funciona?
anecdotal.
Sí, espera, te voy a dar el micrófono. There are also 11 people connected on YouTube. We will ask them if they have questions.
Okay, so first of all, thank you very much for your talk. It was really illustrative, and I'm really looking forward to talking to you afterwards.
Thank you.
My first question is rather simple. So when you were talking about pattern recognition in number theory, the first example was the Model 3 sequence. And you said that any simple algorithm was able to achieve a perfect answer for that problem. My question is, given the tendency of these kind of algorithms to choose the simplest pattern amongst the data that they can see, did you have any experiences by polishing the data set so it's almost the perfect representation of the module 3 sequence, but sometimes you just flip a number and get a 1 instead of a 0, and see whether the algorithm actually predicts the module 3 sequence and takes that hit to the precision because of the simplicity of the answer?
That's a good question. I don't know. Just one, you mean?
Yeah,
like a dot
one
pattern.
or maybe one every 10,000 or one every million numbers.
Just to see whether you can fool it. Interesting.
Or if it just doesn't get full and it's okay, I'm going to lose the accuracy, but I want to stick to my guts and say that this is the module 3 pattern.
My guess is for this problem is simple enough that flipping 1 wouldn't change it so much. I know there are people who design these images where you flip a single pixel and it classifies completely differently. But I think this problem is so simple. It's just it's a linear transformation. So I think you really just need one linear layer. It would do it. I think for this problem it would do it. But it's a very good suggestion to see whether it can muck around to change accuracy for the ones that are predicting very well. Yeah, that's a good point.
Well, then my next question could be, when it comes to actually using machine learning to create conjectures or formulate hypotheses on a certain problem, you were talking about 100% precision. Well, it's actually 99.
Yeah.
So, what's the threshold that you establish to consider that the machine has actually learned something, even though we cannot know what it has learned? Like, what's your precision threshold for these such problems?
95?
95.
I'm just like, yeah. No, me think, yeah. I think because the baseline is so low that, like even in the prime prediction problem, I think if you're doing better than 90%, you know that it's doing something. That's not, it's better than random guess.
Yeah, but there are some problems where you are not using random guess, that you maybe have a baseline from some other heuristic that's also a theory that has not been proven to solve the problem, but you've got like a baseline of 90%, and then would be 95% enough? It's better than any known method, but has it actually solved the problem?
That's right. I mean, the problem, the reason we haven't focused so much on trying to benchmark the accuracy is because we're trying to focus, I mean, I mean we as a community, is try to, in the case that it does better than you expect, in some very vague way, how do you actually get a conjecture out of it?
Yeah.
So we're focusing on that, and we don't really know.
And relating to that, I had another question that you've used a lot of examples of machine learning techniques used to abstract conjectures from problems, and in all of them you establish the problem of interpretability. And if you're using a recurrent neural network, if you're using a deep neural network, then you get really good scores, but you can't interpret what the machine's doing.
Yes, exactly.
When it comes to certain problems, have you tried using simpler models that may be easier to interpret, like the linear models of kernel methods and something like that?
Exactly.
And maybe taking also a hit to the reliability of those methods, but trading it for more interpretability power.
Yeah. Yeah. So far, so far our favorite things have been support vector machines and PCAs, because they are, by far, or even regression, if you luck out. I think the DeepMind one was just, they lucked out, in the sense they completely got lucky. It turned out to be a linear regression problem in the end. And with the memorization, we also just lucked out. It could have been much, much more non-interpretable. You get these big matrices, what are you going to do? But it just so happens you can actually see they're focused on one column. So far, there is a bit of that, right? We are still at the, if you luck out, you can get a conjecture out of it. And so the big problem is, how do you control that? How do you get, I think what you're suggesting is, how do we not luck out and sort of systematically get, you almost need a meta-neural network to train different ones, select the best model. Mathematica does that, but surprisingly, I've just found out that Mathematica does this somehow. For example, when Mathematica does, it's, Mathematica, of course, is one thing good about Mathematica is it's just one function, like classify. When you do Mathematica classify, it randomly goes through all the classifiers, like Bayes, nearest neighbor, k-means, and then at each step, it somehow finds the best convergent one and then goes through that. So what you're suggesting is great. I think this is what we need to do, is to have something that samples through all these different methods and pick out the one that's most interpretable.
Yeah.
I think that's very, very difficult, but we'll get there. I think we'll really get there. This is just the baby step number one.
So that would be my public questions for you.
Thank you.
Do you have some insight into how to connect the two approaches, bottom-up and top-down? So the bottom-up approach is somehow generative, right? Like in the sense of generative grammars and so on. You start with some logical principles inside the language, and then you try to prove. You search for provable statements. The top-down approach, you try to suggest that it's pattern recognition. So it's essentially a classification problem. And you use neural networks as classifiers.
Yes.
Do you have any conceptual insight into how they are connected?
That's a very good question. I think that's really a question for Kevin Buzzard. I think last I was talking to him, I think he was conceiving of a system where you've already got all the bottom-up. There are sentences in this very strange language. To do a large language model on that and find pathways of proofs. I think it's progress. It's work in progress now. I don't know what OpenAI is doing, but probably not that, because I don't think OpenAI has all of the Lean database. But the Lean database, that's at least open. It's open source. You can see it. I mean, it's unreadable. But whatever it is, we have tens of millions of these sentences. And I think it would be very nice. At least one way to do it is to do an LLM on that, and compare, a good proof versus a non-good proof, or an interesting theorem versus non-interesting theorem, and the pathways that generate towards that, and then penalize, make it just play against itself until it's sort of like AlphaZero for Lean. And I think they're actually doing this now. I think it would be amazing. But it's a huge and much less controlled environment than AlphaZero. But it's not inconceivable that we'll get somewhere with that. But I mean, if you talk to Kevin, he says he's actually Kevin is so fun. Kevin he's as fun and colorful as his trousers that he wears all the time, which is as colorful ones. And he says, he doesn't mince any words. He says this is just all bullshit and hype. We're far from Lean taking over mathematics, but it's somewhere in between. I think if we started doing that with Lean, we can give beginning and end point and try to find pathways in between. I think that's a good way to do it.
Good. More questions? Oh, this is very successful.
Okay,
and there
please.
are the people online then.
This question is very down to earth, not as high as your talk, and I'm asking. I'm a person that hasn't tried ChatGPT, so I am naive at that. But I want to know if the answer to this question, if you give to a machine determinant, the square matrix, depending on variables, and you ask the machine to compute the determinant of this matrix, does it do it in any case? Does it tell you a proof? Does it tell you whether where this is found in a reference, or whether the machine found the value this or the other way? So does it tell you what you would expect in a test from a student?
That's a very good question. My feeling is, having played with them, that, well, at least the questions we tried from calculus, ChatGPT is almost perfect. But determinant, I think it's very difficult because it involves some algebraic stuff. But then again, you don't know how much is being trained. So if you have time, we can try one. Let's try one now. Can I try a ChatGPT? And we will just hook it up. I mean, that's a fantastic thing, because we tried something like finding decimal expansion. And ChatGPT 3 wasn't able to do that at all, because you can't really train that. That's a very good question.
Maybe you should connect a computer to this computer, because otherwise
Okay, yes. But
you can use my account.
oh yeah, use your ChatGPT account.
Then this depends on the account. Do you learn from ChatGPT? It's very funny to see how it learns.
Yes, right.
And how it forgets very quickly.
That's right. Well, at least within each session, it's already learning.
Yeah, in each session it learns I think for some days, and then it completely forgets.
Or if you want
Because it depends on the person.
Oh no, yours. I don't remember what my account was.
mine is.
Everyone will see what your account is.
Yeah.
And your
Yeah, and then we're gonna steal it. That's a very interesting one. We're very curious to see. We can try it. What's your favorite matrix?
My favorite matrix, yes, it's on the diagonal one value, and off diagonal another value.
Oh, okay. So just two values.
Yeah.
You mean analytically or numerically?
No. Use symbols. So X on the
I see.
diagonal and Y
Wow.
off diagonal.
Wow. Okay.
This is my favorite matrix for many years ago. Yes, since I have a favorite matrix and it is this one.
Great. We can even just 2 by 2. A, B, B.
No, 2 by 2. No, please.
But let's start with 2 by 2. Just.
We cannot enter because he forgot his password.
Yeah. I'm struggling.
Okay. We'll never
That's the
find
typical
out.
thing.
We'll never find out. I mean, I have ChatGPT on my laptop, but
No, now it works.
it works. Oh, amazing.
No, but it's not logging in. You are blocking yourself.
Oh no, let's
How
not.
are you going to write the many things?
Okay. So this is amazing. I mean, that's a very interesting.
Estás bloqueado a ti mismo.
Uh,
Do you know that ChatGPT makes pictures in TXT?
英文?
In TXT. It makes the
Really?
TXT.
Yeah,
Yeah,
yeah.
I use it a lot.
Oh
I
no,
shouldn't
this
say
how do you type a bracket?
For bracket.
Oh my goodness.
It's this way, yeah, because it's a.
Oh yeah, okay.
You can give a description
Angel can type
as she
ABBA.
No, but you can give the description as you say, and ChatGPT will probably understand it.
X on the diagonal, Y off in every entry off diagonal. X, entry X on the diagonal, AII equals X, AIJ equals Y when
Yes.
I is different from.
Yeah. So X.
J.
Let's try X, Y, Y, X. What's the determinant of that? Computer determinant. Can you see? Yeah, you can see. Right.
Make it bigger, Okay, that's correct.
That's correct. Okay, that's good. So now try 3 by 3.
Make it bigger because
I can try
Okay.
something even more
Control plus.
for the matrix.
Can you even say, can you give me a matrix which is 7 by 7, whose principal diagonal is X and everything else is 0?
Matrix. Ask ChatGPT.
To generate the matrix.
Well,
To
to you say Heisenberg matrix.
Oh, I see. Okay, okay.
Maybe it doesn't know it. If you don't.
Well, and Y.
Everywhere else, yeah.
Everywhere.
Else. Let's see if that even generates.
Yeah. Certainly.
Oh, good. Yeah, good. It even gives you LaTeX.
Now, can you copy the?
So computer determinant.
No, but why do you say computer determinants?
He's so polite.
Yeah.
It's not a person.
Actually, it works, I think.
No, but if you do this in. No, it's a determinant. Yeah, it works.
Is this the determinant?
Ah, interesting. It's not, right?
X a la 7 menos Y a la 7.
Because it's learned that the 2 by 2 case is x squared minus y squared, it thinks the 7 by 7 case is x7 minus y7, making it completely wrong. It says with such confidence,
That's interesting.
like an undergraduate.
Like another.
What is the actual answer? This is 4? This is GPT 4?
No, this is the
3.5.
3.5, okay.
It's the free one. You have 4?
So that answers your question. But this is 3.5. The institute has 4, but I don't have how to log into that.
I was very interested to say that 4 you say it connects to Wolfram?
Yeah.
Alpha? Okay, and this is how it makes the computation.
Yeah. But this one is not
Then
doing.
then it would be correctly because it's just
It would do it.
manipulation.
Yeah.
Algebraic manipulation.
Yeah.
4.
I think it started, right? Maybe 4 above, maybe it's in progress, I don't know. It's connected to Wolfram. It's connected. Yeah.
I think one of the key points here is that it's saying the determinant of the given matrix is calculated by multiplying the elements
oh
of the
my
main
God.
diagonal and subtracting the product of the elements.
Now tell ChatGPT that this is wrong.
Okay, yeah.
This
This
is wrong.
is wrong.
And then he says, I'm sorry, I'm just a formal language, blah blah. And I apologize, let's say.
And now
It's going to give you complete the random stuff. But this is 3.5 to be fair. This is
Wrong again, wrong again. Go to school.
again. The determinant is a very complicated.
just a comment. I'm being very polite with ChatGPT because I heard that if you are polite with ChatGPT, then the answers are better because it detects the polite parts of the statement and it allows you to tokenize the statement better.
Oh really? Wow.
So being polite with ChatGPT is useful because
So I would
it says,
say-
okay,
Will
please.
you ever insult ChatGPT?
No,
I have done.
I am sorry. That is wrong.
No, I'm sorry, no, that is wrong. Go back to school.
It's a very complicated multilinear function. Yeah, I can't type in this.
Maybe you can try, or maybe we can try later.
Yeah, we can try later.
But now, I don't know if there are more questions here.
Yeah.
In the chat, do we have people connected? There were 11 people connected. One of them was me. ¿Tenemos preguntas en el chat?
Let's. I mean, we can do this here. I mean, so.
¿Alguna pregunta del chat para ChatGPT?
Any questions?
The chat at ChatGPT.
Okay, maybe we can continue playing with ChatGPT now after finishing. But if we don't have more questions or comments, then let's thank our speaker again. Thank you.
Thank you very much.